Finally, we get to the proof of the zone theorem. First thing we do is to rotate the picture such that the line L is horizontal. This obviously doesn't make any difference. The next thing is that when I look at the edges in the zone, I can divide them into two big categories: the edges that are intersected by line L and the rest. There are M lines in the picture, so there are at most M line segments that are intersected by line L, because obviously every line in the picture intersects L at most once. Each one of these edges can be counted twice when I sum up the complexity of the zone. In other words, it can be counted in size. So like this this edge can be counted once for this face and another time on this face. Okay. So therefore, when I look at how much these edges contribute to the complexity of the zone, they contribute at most 2m edges in total. So ignore those edges. So now remaining edges, I can count them as either left bounding or the right bounding edges. So what is the definition? So basic definition is that a left bounding edge is the left boundary edge, whereas a right bounding edge is a right boundary edge. So for example, this green edge is a left bounding edge because for this face, the edge rises to the left, whereas this other edge lies to the right, so therefore it's a right bounding edge. Yeah. Obviously, any edge can be categorized as either left bounding or right bounding edge, because when I look at every cell, every edge either lies to the left or lies to the right. Yeah. And then I'm going to prove that the number of left bounding edges is at most 2 times m, and a similar argument gives me that the number of right bounding edges at most 2 times m, and I just sum them up, so therefore I get some bound on the complexity of the zone. So let's just focus on the number of left bounding edges. To prove that, I'm going to use inductions. In other words, I'm going to take out one edge and one line, and by the induction hypothesis I will have m minus 2 times m minus 1 left bounding edges. Then I add the line, and then I show that this only increases the number of left bounding edges by 2, so therefore I can prove that the number of left bounding edges is at most 2 times m. The line that I take out is the rightmost line. So I look at the rightmost line. In other words, the line whose intersection point with the line L has the maximum x coordinate. I take this line out. By induction hypothesis, I have 2 times m minus 1 left bounding edges. And I want to claim that once I add this line back to the picture, this number increases by at most 2. So therefore, in the original picture, I will have 2 times m right bounding edges. Sorry, left bounding edges. Okay. How do I prove this, that this number increases by 2? So let's look at this intersection point. And let's go down and up. So move along the line L1, up and down, until you find the first 2 edges, the first left bounding edges that are split by this line L1. Okay, like this. So the edge E1 is the first left bounding edge that is intersected by this line L1, and this one is also another left bounding edge that is intersected by line L1. Okay. Clearly, the number of left bounding edges increases every time this intersection happens, because the line L1 could split a left bounding edge into two pieces, and which would increase the number of left bounding edges by 1. So in other words, if there are more intersections of left bounding edges with line L1, the number of left bounding edges will increase essentially by the number of intersections. But what I want to prove is that the first intersection above and the first intersection below the line L are the only 2 intersections of left bounding edges with line L1 that will contribute something to the zone of the line L. How do we prove this? I'm going to just prove it for the part of the picture that is above, the below part is similar. So let's just focus on edge E1 here. Edge E1 is intersecting line L1, let's say at this point P. But by definition, L1 was the rightmost edge, which means that this other line, let's call it L prime, is to the left of line L1. So it intersects line L to the left. Okay. So based on these two properties, I can conclude that this region that is over here is not in the zone. In other words, the two lines L1 and L prime isolate this region from the zone of the line L. This is because these other three quadrants are intersected by line L, so this quadrant cannot be intersected by line L, because a line L cannot intersect all the four quadrants that are created by drawing two lines in the picture. Okay? So that part of the picture is not in the zone. So therefore, there cannot be any left bounding edges on this part of line L1. Okay, and also over here, because for an edge to be left bounding, the cell to its right should be in the zone, and the cell to the right of all of these cells over here, by definition, is in this area, which is not in the zone of line L. Okay. So this means that the only edge that can be in the zone of line L is this edge E1. So therefore, by adding line L1, I will increase the number of left bounding edges by at most 1. I can increase the number of left bounding edges by at most 1 below. So therefore, the number of left bounding edges increases by 2. And then when I add all these numbers, it follows that the number of the zone of the line L has at most I guess 6 times m complexity, which is O of m. Yeah, so basically this part E3 cannot be in the zone of the line, in the zone L, so it's not, so it does not increase by that one. So the constant that we get here are slightly different from the constant that we have in some other theorems. This is because a particular definition that we have here. So here I do not count these edges as part of the zone, because I define the zone of the line L as the total complexity of the cells that are intersected by line L. In some other description, in some other, like if you look at this zone theorem on the internet, sometimes people count these edges and they also count them twice because it's counted inside this face and this face. So here we're counting things slightly differently, so therefore we get slightly different constants. I think in the book this 2 is actually a 5, which would be the case if you count those two edges as well as these edges twice. So the constants are slightly different, but the proof is more or less the same. And the main idea is that we have this isolation that happens between from the zone by having these two lines intersecting in this form. So that essentially proves the zone of the theorem, which would give us the analysis of the algorithm that the arrangement of n lines can be computed in n squared time, which is optimal.